This is the second part of my screencast for the first week. This is for the Chapter 2 stuff. Let's see. So in Chapter 2, we really go into multidimensional waves. We need to understand what's happening there. So I have this movie here. We see some excitation happening in the middle, and then the illusion of something moving away. Let's be very clear. Pick your favorite dot. How about this one? It's just moving up and down and up and down. That's all the dots are doing. They're just moving towards the center and away from the center. Here's another one. Towards the center, away from the center. Here's another one. Towards the center, away from the center. That's all they're doing. There is no single particle that is making the journey from the middle all the way to the outside edge, but there's clearly this illusion of something moving out. That's the wave. So we're going to talk about two-dimensional waves here in this section. There's also this YouTube movie, which I'm not going to click on right now. I very strongly encourage you to look at it. This talks about double slits and their importance to the quantum world. It's sort of a cartoon, but done really well, frankly, and I think even your students would enjoy it too. Frankly, I enjoy it. So I would recommend you look at it. It's going to be helpful for this chapter, certainly, but really immensely helpful for the next chapter. So I'll probably just put the link in there as well. Okay. So two-slit interference, also known as the double-slit experiment, we want to try to understand what's happening with that. So let's see here. I'm going to make this just a little bit bigger. There we go. So here we have two slits. We have to imagine a wave coming from the left, way over here, and then once it goes through these two little slits, it creates their own circular waves coming out here. And then both of those waves will head towards a target. If they head towards anywhere on this line, specifically this point right here, well, equidistant. This point is the same distance away from here as it is from here. So those waves would arrive at the same time. So when one's up, the other's up. That's doubly up. When one's down, the other's down. That's doubly down. So you get a very high intensity there. Let's look at this point here. At this point, you're a little bit closer to this one and a little bit further away from this one. So there's a path difference. And in fact, if we go all the way up to here, y, where it's drawn, this dashed line is longer than this dashed line, right? Just by looking at it, you can tell that. How much longer? Well, make an isosceles triangle. Drop this line in here and make an isosceles triangle, which you've just made this leg of the triangle the same as this dashed line here. That means that this wave has to travel that much further. Well, you can do some geometry to figure out how big that is. Frankly, it gets a little ugly to figure out exactly how much longer that is. But in the case when capital D is much larger than lowercase d, it turns out that you make the approximation that this angle theta, which is kind of the same as this angle up here, all of these angles are quite small. And you also make the additional assumption that this theta and this theta prime are the same. That's what's being said here. And then this extra little distance, delta, is just d sine theta. Very simple. D, the space between them, sine of the angle. Well, how do you figure out that angle? I mean, you can't go in there and measure that. My God, if we could do that, we'd see the slits really good. But if we claim that theta prime is the same as theta, then, well, for small angles, tangent of theta is roughly equal to sine theta, roughly equal to theta. So it's just y, which is easy to measure, over d, which is hopefully easily to measure also. Now, if that path difference is an integer number of wavelengths, then the wavelength is, pulled one full wavelength behind. You can't tell the difference. You're going to have a peak. If it's half a wavelength or an odd number of half wavelengths, it's going to be a minimum. Why an odd number of half wavelengths? Because if it was an even number of half wavelengths, it would be a full wavelength, and then you'd get a peak here. That's all I wanted to say there. Okay, so light does this. And when light does it, you can actually do it to measure the wavelength. You can do it with rulers. I mean, you can shine light on a ruler that has really fine spacing on it, and look at the pattern you'll see on the wall, and measure the pattern, and voila. You can actually see the interference. We'll probably do that experiment next summer. So light does this. Next chapter, we're going to learn about some other stuff that does it. And if you watch that YouTube movie, you'll understand it a little bit better. So diffraction. We need to understand that even a single slit is going to cause light to bend a little bit. Let's look at this picture first. Sound instead of light in this case. Somebody on stage with a guitar sending out sound, and it's bending around things, and it's bending when it goes through this little thing here. And also another example is a marching band. You have a bass drum and a flute player. The bass drum's sounds are very widely spaced wavelengths. If a wave encounters an obstacle, like this corner here, this intersection, the same size as the wavelength, quite a bit of bending will happen. quite a bit of bending will happen, which is if you're around the corner, you will hear the bass drum long before you'll hear the flute. See, the flute has this very short wavelength spacing, very, very short. It doesn't bend around these corners. That's why you always hear the bass drums of marching bands first, because it bends around better. In the book, it talks about this principle called the Huygens principle that says that every point on a wave front can be thought of as the source of a teeny tiny little wave that works together with all the others to reinforce the wave. I want to show you a movie of that. This is actually subtly just a little bit different. Here I have a red line going from the bottom to the top, and a bunch of black dots. I wrote the program that does this. It's very simple. Draw a red line that goes from the bottom to the top at a constant speed. If a dot gets hit by the red line, it should start drawing a circle. It should draw that circle so that it grows at the same speed that the red line travels at. Very simple. Then I just draw all the circles. And you'll notice something really interesting. All of the black circles work together to reinforce each other in the original direction of the red line. And the circles don't at all work together in any other direction. Why? Because I totally randomly spaced these things. We're going to see a lot more of movies like this next summer. But the notion is you can see how tiny little circles can reinforce a flat line, which is being seen right here. So that's diffraction. Finally, we'll end with optical resolution in this chapter. If light goes through a teeny tiny hole, it makes a big smudge here. The size of the smudge is inversely proportional to the size of the hole. Bigger the hole, smaller the smudge. This is not what you would initially guess. A tiny little hole, imagine sound or light or any kind of wave being forced to go through a tiny little hole. It immediately spreads out and you get a big old splotch here, which is why the Hubble telescope with a pretty big hole gets much better resolution than your pupil. Let's understand that resolution. Here's a couple of splotches. Well, let me go back. Hang on. Let's imagine that you have two lasers, one coming in at the one that's drawn, another one maybe at a slightly different angle. Well, if I put another smudge down here, it might sort of blend in with that smudge. And can you really tell them apart? Well, that's when you go, well, here's two that you could probably tell apart. Here's two that don't really look like two anymore. It just looks like one. And we'll call this something called the Rayleigh criterion. Well, when it's just dipping down like that, all right, you can tell them apart. That's where this 1.22 business comes from, by the way. But what happens if, let's say this is with your eye. If you use the Hubble telescope, every single one of these dashed lines would be a lot narrower because you'd have smaller smudges. If they're a lot narrower, you might actually be able to distinguish those two. So the Hubble telescope can distinguish a lot better. And I think that's it for this one.